So we've been dealing with rational equations, and we know how to graph rational equations and list their attributes, but now we're going to start talking about inequalities. And when we deal with inequalities, we're doing greater than, less than, greater than equal to, less than equal to, and not equal to. And whenever we're doing that, our answers are going to involve interval notation. So we're always going to write our answer in interval notation. Anytime you're solving anything with an inequality symbol, the answer will be in interval notation. So we've got a couple of steps here. We're going to write the inequality. So the rational expression is on the left side and 0 is on the right side. And this is important. So we're always going to want f of x in some relation, whichever inequality we have, equal to 0 or in relation to 0. We're going to be looking for the zeros as well as the undefined values. And then we're going to set them on a number line, create some separate intervals, and then this is the part where we can test. And we did this before in class. We tested to see if the value on each interval was above or below the x-axis, greater than or equal to 0, less than or equal to 0. Greater than would be above, less than would be below. So we'll look at an example here quickly. This one's already set up in relation to 0. So you'll notice that 0 is on the right side. And we're talking about this here and saying that this rational expression, x minus 3 over x plus 1, needs to be less than or equal to 0. And less than or equal to 0 says to me that it needs to be below or touching the x-axis. So if we're doing this problem and we want to determine what the x-intercepts are, we know that the x-intercept comes from the numerator. Okay, so the x-intercept is going to come from taking that x minus 3 and setting it equal to 0. And if we do that, we're going to get x equals 3. So that means 3, 0 is an ordered pair on my graph. And we'll also need to look at our undefined value. And the undefined value is going to occur for x plus 1 being equal to 0. And so at x equals -1, it's undefined. And really, we could write that with a not equal to through there. So we've got x equals -1. That is a value I'm going to plot on my number line. So I'll come over to my number line space. I'm going to plot x equals -1. And I'm going to plot x equals 3. So I have these two values. We need to choose a test value on each interval. And it can be any value you want it to be. All right, so less than -1, I'm going to use x is -2. Between -1 and 3, x is 0. And greater than 3, maybe x equals 4. All right, so I'm not choosing any values that are ridiculously larger than I need them to be, just large enough that I can test them. And I want to test them in my original equation. All right, so if I plug -2 minus 3 over -2 plus 1, that ends up simplifying to -5 over -1 or +5. And +5 is not less than or equal to 0, right? And because it's not less than or equal to 0, then I'm not going to include that region in my solution set. So I'll test again for x equals 0, 0 minus 3 over 0 plus 1, which gives me -3. And then when I compare that to 0, is -3 less than or equal to 0? And the answer is yes, it is. So that means I can shade on this region. This region is going to be part of my solution set. And then lastly, we'll check at x equals 4. 4 minus 3 over 4 plus 1. That gives me 1 over 5. If I compare that to being less than or equal to 0, it's not. Right? And because it's not, I'm not going to include that value in my solution set. So any number between -1 and 3 are going to be solutions to the inequality that we were originally given. But we have to ask ourselves, can we touch? Are we allowed to touch? So when we go back and look at what was given right here, you can see we have less than or equal to. So equal to lets me know that I can be touching that point. So it means I'm allowed to include 3. 3 is a 0, so I'm allowed to touch it, right? So I can use a solid dot there. But -1, we would think, okay, well, I'm going to use a solid dot for -1. But am I allowed to use a solid dot for -1? So what you want to remember is that -1, we're not allowed to touch that. -1 is undefined. So when I'm marking that on my number line, I'm going to draw a nice open circle here to indicate we cannot touch that. So in this situation, my solution set is that any x value between -1 not touching and 3 inclusive is permitted. So this interval represents the correct solution set. So I want to take this thought process a little further. I'm going to rewrite our problem here and help us think about the graph. So if we were to go and graph this on our graphing calculator, then we would go over to our y equals and we would type in x minus 3 divided by x plus 1. And graphing that, pulling that up, you're going to get something that has a vertical asymptote at x equals -1 and an x-intercept over here at +3. The horizontal asymptote for that graph would be at y equals +1. And so we're using some review knowledge and the comparison test to come up with that horizontal asymptote. And we'll see a curve that bounds up to the asymptotes down here in the bottom right and up here in the top left. And so, again, we're looking at this and we were trying to solve where is this less than or equal to 0. And less than or equal to 0 means below and not touching the x-axis. So where's the graph below and not touching the x-axis? Everywhere between -1 and 3. This is where I end up with a graph that is below. Right? You see that part of the curve there. So we have a graph that's below the x-axis. Everywhere else, the graph is above. So if we had had a greater than problem, we would have written this interval differently. So I've skipped to one more example that we're going to do. 4x minus 5 divided by x minus 2 needs to be greater than or equal to 3. Now, as we said before, we want this to be in relation to 0. So 4x minus 5 over x minus 2. I'm going to subtract that 3 to make it in relation to 0. We always want 0 on the right side. So as I work through this, I'm going to need to combine those and make them into one fraction. In order for me to do that, I've got to get common denominator. So I'm going to take that 3 and multiply it by x minus 2 over x minus 2. And doing that is going to allow me to add these two terms together. And what I'll end up with once I do that multiplication is 4x minus 5 minus 3x plus 6 over x minus 2 greater than or equal to 0. Combining like terms, I end up with x plus 1 over x minus 2 is greater than or equal to 0. So the two values I'm going to use here, I'm going to pull 1 out of the numerator, that is my 0, and then I'm going to pull another value out of the denominator, and that is undefined. Right? So my 0 is going to be at x equals -1 is my 0, and x equals +2 is undefined. Marking both of those on my number line, -1 and +2, I can choose a test value now on each interval. And I might test x equals -2, x equals 0, and x equals 3. And we're going to test each of these three numbers, -2, 0, and 3. They're all going to go into this equation we have down here at the bottom of the page. So we took what we were dealing with and rearranged it so that it was in relation to 0. And now I'll test each of those numbers. And testing them, -2 plus 1 over -2 minus 2, that gives me -1 over -4, or +1/4, which is greater than or equal to 0. So this region to the left of -1 is going to be included. Am I allowed to touch -1? It is a 0, so that means it's a point on the graph. And because our function has a greater than or equal to symbol, that lets me know I can draw a solid dot at x equals -1. So similarly, 0 plus 1 over 0 minus 2, that gives me -1/2, which is not greater than or equal to 0. And then we'll do it with 3. 3 plus 1 over 3 minus 2 is 4 over 1. +4 is greater than 0, so we do include that region. So we're going to shade everywhere to the right of +2. And we have to ask ourselves, can we include 2, right? Do we put a solid or a closed dot right here at x equals 2? And if we only thought about the original inequality we were given, we'd say, oh, well, it must be a solid dot because it can be equal to. But what we have to remember is where that 2 came from. 2 was a value that came from the denominator, which means it represents an undefined value that the graph will never touch. And because we can't touch those undefined values, they'll create 0 in the denominator. We know we're just going to have an open circle here at x equals 2. So my solution, the way I would write my answer, is that x is in the set from -infinity to -1, bracket to include it, union, parenthesis 2, to +infinity. And that is my interval, which represents the solution.